In this video, we are going to learn on how to use Macaulay's method to determine the deflection and slope of beams. We are going to look at the boundary conditions of beams as well as the rules that you need to follow when you're using Macaulay. Now let's start with our boundary conditions. The boundary conditions are basically the conditions in which beams deflect on. For example, let's assume we have a cantilever beam. If you apply a force at the end of this beam, the beam is going to bend or deflect downwards like this. And at this point right here at the end, that's where you're going to find your maximum deflection as well as your maximum slope. The deflection is basically the distance from the natural position to the deflected position. And the slope is basically the gradient of this line. The boundary condition at this point where the cantilever is, the deflection is going to be 0 and the slope is going to be 0 because there is no deflection or slope at the wall side of the cantilever. Now let's look at the built-in beam. For a built-in beam, if you apply a force somewhere about the center, your beam is going to deflect downwards like this. The deflection at this point is going to be maximum, which is at the turning point. And the slope at this point is going to be 0. The deflection at this point, at the support, is going to be the same as the ones in the cantilever. Now let's look at simple supported beams and overhanging beams. For a simply supported beam, our beam is going to bend downwards like this, and at this point our deflection will be max and our slope will be 0. At the supports, our deflection is going to be 0 and our slope is going to be max. Now let's look at an overhanging beam. Our overhanging beam, when the force is applied, is going to bend like that, and at the ends our deflection is going to be max and our slope is going to be max. At the supports, our slope is going to be max and our deflection is going to be 0. At the turning point, our slope 0, deflection max. Same. These are the boundary conditions that you're going to face that you have to take into account when using Macaulay's method. Now, let's look at the rules that you're going to apply when using Macaulay's method. The first rule states that the brackets are to remind us that these are Macaulay's terms. Now, let me throw a simple example. Let's assume we have a cantilever. We have a point, a force acting. Let's say this is A and this is B. The first thing we're going to do when using Macaulay's method is we're going to introduce a new point starting from any side of the beam to just before the final point. This point can be anywhere in this span, and it's going to be at an x distance. So now, before we go back to the first rule, let's look at the second rule. The second rule states that the bending moment equation should cover the full x length. So basically, you are going to take your moments clockwise positive at this point, meaning it's going to be our negative p times x minus a. The distance from P to this point right here is going to be x minus a, since we know a, but we don't know where this point is. The third rule or third condition states that the flexural rigidity must be constant. This is basically our E times I. The fourth rule states that if our bracket x minus a is less than 0, then that term must be ignored. There's going to be a point where you're doing your calculations and you're going to have an equation. Let's assume this equation right here. You're going to say let x be a certain value where our slope is 0. We'll be using our boundary conditions to find a certain value, an unknown value. So in this point, let's assume that we're going to have our minus p. Let's say our x is 2 and our a is 6 plus a. What the fourth rule basically means is that if we have something like this where the bracket x minus a is less than 0, we ignore this whole part. We won't use this term in our calculations. The fifth rule states that the term including x minus a must be integrated with respect to x minus a. So basically, when we integrate our minus p x minus a, we're going to keep it as it is, as one term, instead of separating it. It's going to be squared over 2. And then the final rule states that do not expand any of the terms involving the brackets, which basically goes with the fifth rule that we keep this as one term. We do not break or expand this bracket. We keep it as it is. Now, for Macaulay method, we're going to use 3 equations. The first equation is going to be our bending moment equation. The second one is going to be our slope equation, which is the integration of our bending moment equation divided by EI. The third equation is going to be our deflection equation, which is the integration of our slope equation divided by EI. In the next video, we're going to look at an example on how to tackle Macaulay's method. Now, before we end, Macaulay's method can be used to solve any problems on both statically determined and statically indeterminate beams.